we already talked about the binary sort, selection sort, insertion sort, and we noticed that all of them, they're going to have the complexity of order of n2. Today we're going to talk about the other types of algorithm, which are going to perform a little bit better, and those are merge sort, quick sort, and we're also later going to talk about the heap sort. But merge and quick going to be the focus of today's session. First, we're going to start with merge sort algorithm. So merge sort algorithm is one of those algorithms that is using the divided and conquer strategy. Instead of reducing the size of the problem every time only by 1, we're actually going to reduce the size of the problem by half, right? So we kind of see this type of the algorithms when we deal with binary search, and we notice that when we can use that by dividing the problem every time to the half. So here we're basically doing the same thing. So I'm going to just do some sort of analysis before on these types of algorithm before I go and talk about the merge sort specifically. So I put this, the things I want to talk about on this Excel sheet. So when we're trying to solve these types of problems that, basically divided and conquer problems, originally the size of the problem that we start to work on it, like maybe the number of elements that we're trying to sort in the case of a merge sort is n. We have n element in the list that we're trying to sort. Divided and conquer strategy, every time we divided them with half, and then we keep doing it. We divide it by half again and a half again and a half again until we get to a point that the size of the problem is going to be only 1. So like what we did in the binary search, right? So first we divided by half, and then we divided again by half, and then we divided again by half, until we get to the point that we only have one single element, and that's probably, if lucky, is going to be the key that we're looking for. The sorting algorithm is also going to do the same as strategy, but the difference is that in the search, in the binary search, every time that we're dividing the problem to half, we get rid of the rest of the problem completely. So basically, if you look at it as a tree, like what we have here, this, what I have in the left side, are the levels of the tree, right? So, or the height of the tree. At this point, when I only have one element in this tree type of structure, the height of this tree is 0. So I have a big problem, a complex problem of size n. I only have one problem. So here's the number of problem I have. I only have one problem. The size of the problem is n, and I'm in the height 0 of this tree, or the level 0 of this tree. Then I go to the next level. I start dividing and conquer, and so the next level I have 2 problems. The size of each problem is going to be the half of the size of the original problem, and I'm in the level 1. In the next level, I have 4 problems, and each problem now is going to be divided by 4, by half, right? So it's going to be half size of the previous problem, and so on. So if we keep going, at some point, which is going to be the height of this tree, and we don't know when we get to that height, depends on the number of elements. At the height, we know that we're definitely going to have problems of size 1. But how many problems we're going to have? So let's go back up here. When I had one problem, the size of my problem was n. So the overall, the total problem that I had to solve, the total size of it was still n. So look at here, I created this table. So it's going to be one problem, and the size of that problem is n. So the total problem that I have to solve is still the size n. When I get to level 1, I have 2 problems, and each of them is going to be an n over 2. So the total is still going to be n. When I get to the level 2, the number of the problem I have is 4. The size of each of those is n divided by 4, or n over 4. And so the total size of the problem is still going to be n. So no matter what, when even we get to this point, that the size of my problem is only 1, still I'm going to solve the overall type of problem that is n. So that means although the size of the problems are 1, but I should have n of them. So the overall size of these problems still stay at n, right? So that means that this level, as you see on this picture, at this level, at the last level of level H, I'm going to have n problems that each of those problems, their size is 1. So we're going to put all of this data that we identify from this tree on this table. So those are the levels that we identify all the way to the level H. These are going to be the size of the problems. These are going to be, sorry, the number of problems. This is going to be size, and this is overall. We know the overall size is always going to stay n, no matter what. So now let's look at here a little bit more in depth. So when I'm in the level H, as we keep looking at all of these and we do analysis, when I'm in the level actually 0, the problem I have is 1. So that means it's kind of like 2n basically divided by 2 to the power of h, right? Because 2 to the power of 0 in this level is going to give me 1. So the next one is going to be 2 to the power of h. H is 1, so that's why it's 2. The next one is 2 to the power of 2. So 2 to the power of 2 is going to give me 4. The next one is 2 to the power of 3. It's going to give me 8. The next one is 2 to the power of 4, which is going to give me 16, and so on and so forth. So the relation between this level of the height of the tree and the number of problems is basically going to be the 2 to the power of h. When we get to the level h, we would like to have n problems of size 1. So we know the size. The only thing we don't know is that, okay, what is h, right? So that's the thing we don't know, what is the value of the h. But I know that 2 to the power of h has to be n. That's for a fact. I know. Why? Because I want to keep the overall size of the problem n. And since I know that I have problems of size 1, I know I have to have n of them. So 2 to the power of h has to be n. So if I want to identify h, I'm going to do the log of base 2 for both sides of this equation. So it's going to be log 2 to the power of h and log n. So these logs are base 2. So, if you remember the logs, so if you have 2 to the power of something, then you can say that thing multiply that log, right? So it can go to become the multiplication. So it can be converted to that. So that's giving us the h multiply log 2 is equal to log n. And we know that log anything to the base of that thing, which here we have log 2 base of 2, it's going to be 1. So log 2 base 2 is 1, so that's going to get out of our equation. And the only thing and h multiplied 1 is going to be h. So what we're going to get here is that h is going to be log n. What this tells me, it's telling me a formula that is, basically is going to give me the value of h based on the number of elements or basically the size of the problem. So if the size of the problem grow, the height of this tree, back to the growth and the big O notation, right? So if the number of the elements, which is n, is the size of my problem, grow, double, for example, the height of the tree, or basically the levels that I have to divide it, my problem, until to get to the size 1, is going to be only grow by log n, which is a very good thing, right? So I'm talking about only one branch of this tree at this point, right? So it's just in one single branch of this tree, I'm going to have the problem of log n to be solved, right? So, and that's exactly what we had in the binary search, right? We're just going to one branch because every time we break the problem to half, we get rid of the rest of this completely. So in the binary search, you only have to go through one branch of this 3, and that is going to give me the log n. But in the sorting algorithms, we're never going to get rid of the half of this other part of this problem. Even if we divide it by half, we're still going to keep both halves. So we have to solve all of those. So that means I ended up with having n different branches, right? So n different branches, and for each branch, I have to basically work log n. So the complexity of each of them is log n. That means I overall going to have a complexity of n log n because I have n branches. Solving one branch is going to take me log n times. Solving n branches is going to take me n log n times. So these algorithms are all divided and conquer strategy. They're all going to act as n log n. So of course, the binary search is going to do divided and conquer, but every time it's going to completely reduce the size of the problem. It's going to get rid of the other part of the problem completely. So that's why it's only going to go over one branch of this tree, and that's going to be log n. But in the sorting algorithm, we're not going to get rid of that. And so we're overall going to have a problems of n log n size. So that's the, a little bit of analysis of how these algorithms are going to be working and why their performance is n log n. And that's the fastest we can do in any sorting algorithm for a random data. So this is how the merge sort works. Again, we're going to do divided and conquer. I said, whatever we have as the element that we're trying to sort, that's the original area, the size of the problem. We're going to start dividing it by half, right? So we're splitting it, and at some point we stop the splitting. And as you can see, we have now problems of size 1. How many? Exactly how many we had on the original list. So original list here, we had one list of 8 elements. When we're done with the splitting, we have 8 lists that each of them only have 1 element, right? So here we have a 1 multiply 8, and here we have 8 multiply 1, right? So 8 problem of size 1. And then when we're done and we get to this point, we basically can tell that each of these individual lists that we have, because their size is only 1, they're already sorted, right? So 2 by itself, the array list of size 1 is already sorted. So that means we now solve the problem. We have each problem that we have, it's already sorted. But we have 8 of them, and now we have to start merging them. So that's the conquer part, right? So we start merging them. So as we merge, actually the sorting happening here in the algorithm as we merge them. So as we merge, we're going to create a larger size array, and we're going to sort them, right? So what we have to do is we have to compare them, see which one is bigger, which one is smaller. First, we put the smaller in the new list, and then we put the bigger one. So here we have 2 and 9. So 2 and 9 is going to go to the list. Then we have 4 and 5. So 4 first go to the list, and then 5 is going to go to the list. And then we have 8 and 1. So 8 first go to the list, and then, sorry, 1 first go to the list, and 8 go next. Then we have 6 and 7. So 6 first go, and then 7. So we keep doing comparison. So how we do the comparison? We have 3 different indexes that we have to compare them with each other. First is going to be the index of the list 1. Then it's going to be the index of list 2, and then it's going to be the list of the list 3, the one that we're going to put everything there at some point, right? So let's merge the next level. this is happening recursively, as you can imagine, right? So this is a completely recursive algorithm. So divide and conquer strategy is mainly also focusing or working for recursive types of algorithms that you can basically call the same method over and over and over again until we get to stopping point, right? So in this algorithm, we keep calling the split method over and over and again until we getting to a point where we can stop, and we stop calling the merge method, and we keep going until we're done with all the merging. So in the next, I want to go all the way to the last level of the merging. Here. So we have 2, 4, 5, 9 in a list, and we know that sublist is sorted for sure. And we have another sublist 1, 6, 7, and 8, and we know for sure that's going to be sorted. So we'll start merging them. So we have a larger size array that we have to merge these two small or half size array into it. So first we're comparing 2 with 1, the index of the very first list, the first element of it with the first element of the second list. We find the smallest one and we put it in the list number 3. Then we have to increment the value of these indexes, right? So index of list 2 and index of list 3, they're both going to increment it. Then we're comparing 2 with 6. So 2 in this case on the list 1 is the smallest element. So that is going to go to our list. And then we now have to increment the index of the list 1 and the index of the list 3. Then we're comparing the value of 4 and 6. 4 is a smaller, so we put 4 in the list 3. We increment the list 1 and list 3 index. Now we have 5 and 6 that we have to compare. 5 is smaller than 6, so we're adding 5 into the list. We increment the index of list 1 and list 3 again. So now we have to compare the 9 and the 6, and 6 is smaller, so 6 is going to go to list 3. And then we're going to increment the value of index of list 2 and list 3. So then we're comparing the 7 with 9, and still 7 is smaller than 9. So we're going to add 7 to list 3. We're going to increment the index of list 2 and list 3. Then we have to compare 8 with 9. 8 is smaller than 9, so 8 is going to go to list 3. The index of list 2 and list 3 are going to be incremented. And the last one is going to be the list. Basically, the list 3, the list 2 is done, right? So when we increment the index of it, it's going over the size. So we know we're done with the list 2. So we don't have to do any more comparison because we're done with one of our lists. So whatever is in the list 1 now, in this case, has to be just copied into the list 3 until we're done with the indexes in that list 2. So we're just going to have a loop, and we're going to move everything from the list that is still have remaining data to the list 3, and we don't need to do any comparison anymore, right? So that's how this algorithm works. So basically,